In the previous chapter, we looked at how metals and nonmetals come together to form ionic compounds. They do this to, of course, meet the octet rule, to become more stable, to become like noble gases. And the best way for metals to do this is to give up their electrons to the nonmetals, which need more electrons. Now, in this chapter, we're going to look at bonding between nonmetals. So the bonding that connects one nonmetal atom with another nonmetal atom, what we call covalent bonding. Now, we're still trying to meet the octet rule here. So our nonmetals still want to gain electrons to try to become like the next noble gas. However, in order, if you have two atoms that are bonding together that are trying to gain electrons, what effectively happens is that they wind up sharing these electrons. And that is where the name covalent comes from. The word covalent means to share valence electrons, and that's what's happening here. Now, instead of having a huge network of positive and negative ions like we see in ionic bonding, here we have clumps of atoms that are connected together by these covalent bonds. These groups of atoms that are covalently bonded together are known as molecules. Okay, so you've probably heard that word molecule in relation to chemistry. Well, here's where it actually applies. A molecule is a group of covalently bonded atoms. Now, the simplest molecule you can make is hydrogen. Now, hydrogen atoms by themselves, of course, are not stable. They need to engage in bonding like any other non-noble gas. Well, two hydrogen atoms will come together to achieve some stability. Okay, so they each share their one electron. They kind of pool their resources together. So they effectively wind up sharing these two electrons, each of them contributing one. Now, in that sense, they're like helium. Helium is a noble gas with two electrons, filling up its 1s orbital. And so this hydrogen molecule kind of mimics that. And that's why a hydrogen molecule is much more stable compared to individual hydrogen atoms. Right. Now, in the chapter on ionic bonding, we saw that we use subscripts to show the number of atoms or number of ions that we need to balance each other out in our formula. In the case of covalent molecules, we still use subscripts, but in this case to show the number of atoms that we find in a single molecule of the substance. So here we have two hydrogen atoms making up a hydrogen molecule, and the formula for this hydrogen molecule is H2. Right? So the 2 in there refers to the fact that there are two hydrogen atoms in our one hydrogen molecule. Now, we call these types of molecules diatomic molecules. They are molecules made up of two atoms. So hydrogen, of course, is not the only element that does this. A lot of elements will form diatomic molecules to make more stable versions of themselves as elements. So we're not even getting into like compounds yet. But sometimes atoms will covalently bond with themselves to make these stable molecules. All right, so for example, here we can see examples with fluorine, oxygen, and nitrogen. All of these exist as diatomic molecules. Now, the number of electrons they have to pool together will vary depending on how many electrons they need as well. So an oxygen atom, which needs 2 electrons to meet the octet rule, will actually wind up contributing 2 of its own electrons to share 4 electrons in total between 2 oxygen atoms. So that's why oxygen, for example, has a double bond between the oxygen atoms, making up the molecule. We'll get into more of how this happens in a little bit when we start discussing Lewis structures. Okay, but for now, I'm just pointing out how you can share different numbers of electrons between your atoms in a molecule. So you should know which elements form diatomic molecules. In later chapters, when we start looking at chemical reactions, where we start representing these these molecules in chemical reactions, if you ever hear one of these elements referred to by name, you should be ready to write down their formula as a diatomic molecule. So remember that all of your halogens, okay, so that's the elements in group 17, fluorine, chlorine, bromine, and iodine. I've left out astatine just because you're not going to get asked about astatine. Like, literally no one knows anything about astatine. It's too rare to study. But anyway, halogens are all diatomic molecules. In terms of the other elements, we've also got oxygen, nitrogen, and hydrogen. Okay, so remember these 7 elements that kind of make a 7 in your periodic table. They exist as diatomic molecules. So if you hear nitrogen, realize that it's referencing an N2 molecule. If you hear chlorine, realize it's referencing Cl2 molecules. Okay. Now, what about compounds? Well, the same aim applies here. Our atoms still want to meet the octet rule, except hydrogen, of course. Hydrogen's weird and just wants to follow a duet rule. It wants to be like helium. So let's look at this example here with methane. So methane has a carbon and 4 hydrogens. Now, why does it need 4 hydrogens? Well, carbon in group 14 has 4 valence electrons. So it needs 4 more electrons to become like a noble gas to meet the octet rule. So since each hydrogen contributes only 1 electron, the carbon needs 4 hydrogens to get the 8 electrons around it to meet the octet rule. So let's talk about how to draw Lewis structures. These are pictures of molecules representing the valence electrons that we see, that we want to keep track of in our molecules. Now, when we do this, when we show these valence electrons, we're going to represent them either as shared electrons between 2 atoms, and we'll use a line to represent a pair of shared electrons or a covalent bond. And we have what are called lone pairs of electrons, also known as non-bonding electrons or unshared electrons. These exist as pairs of dots, and they belong to just one atom. Okay, so they'll be put next to one atom. As the name implies, they're not shared between 2 atoms. Okay, so we will use the symbols for our elements to show the atom in question, and we'll use either these dots or lines to represent the valence electrons of these elements. So here's an example. Here, let's say we're trying to draw the Lewis structure or electron dot formula for fluorine. Now, fluorine is made up of 2 fluorine atoms. Now, fluorine atoms are found in group 17 of your periodic table, so they have 7 valence electrons. So here are our 2 fluorine atoms, and they want to reach the octet rule. So they want to share electrons so that they have 8. Well, if we look at the fluorine on the left, it has 7 electrons. It just needs 1 more. So it shares one of the electrons with the fluorine on the right, which in turn kind of pulls in one of the electrons from the fluorine on the left. So those 2 electrons are the ones that are shared, in our covalent bond. So we represent those 2 shared electrons with a single line between our fluorines. Okay, so I prefer drawing covalent bonds using a line like this. If you go back a few slides, you may recall pictures of fluorine, oxygen, and nitrogen molecules where we just showed the shared electrons as dots. You might see Lewis structures drawn that way. I find that typically people find those a little bit more confusing, just because it's sometimes hard to distinguish between those and lone pairs. They all look very similar. So personally, I prefer drawing Lewis structures with a line representing that covalent bond. Okay, it's a little bit easier to see which electrons are being shared versus which electrons are lone pairs belonging just to one atom. Okay, now the only thing you've got to watch out for, of course, though, is remember, even though this is one line, there are 2 electrons in that one line. Okay, so that's the distinction I want to make here. We have bonding pairs of electrons, also known as covalent bonds, and we have lone pairs or non-bonding electrons. Okay, so these are electrons that belong to just one atom. So you could draw Lewis structures by counting out the dots representing their valence electrons and trying to pair things up like we did in the previous example. However, I've found that over the years, students run into issues trying to draw molecules that way, especially when it comes to an unusual number of bonds or things like double bonds and so on. These throw little curveballs for most students. So I've kind of crafted a different method for drawing Lewis structures. If you covered Lewis structures in high school or in another course and you find that you prefer that other method of drawing Lewis structures, by all means, please use whatever method you're comfortable with. Okay, but just know that this might be a slightly different method than you might have been taught in another class. Okay, when it comes to Lewis structures, ultimately you want it to meet two main requirements. You want every atom to meet the octet rule, okay, with of course the exception of hydrogen, which follows a duet rule. It only needs 2 electrons, but all the other atoms have to have 8 electrons when you're done drawing your structure. Okay, now there'll be a few exceptions to this down the line. We'll talk about exceptions in a little bit, but for the most part, most atoms need 8 electrons around them when you are done drawing your Lewis structure. Okay, regardless of how many valence electrons they have as lone atoms, when you're drawing your molecule, they should have 8 electrons around them. The second rule is that these molecules should represent the right number of valence electrons that these individual atoms bring to the table. Okay, if your molecule does not show this, if your Lewis structure does not show the right number of electrons, that means that you've drawn it slightly incorrectly, but you can fix it by adding in double bonds. So essentially, if you have the wrong number of electrons in your drawing, that's a hint that you need to, your molecule probably has double bonds or maybe even triple bonds. Okay, so we'll talk about that scenario in a little bit. So those are the 2 key things you want to watch out for. Now, quick note here about the issue with having the wrong number of electrons and needing to put it in double bonds. I really recommend drawing these with a pencil. You'll find that you're going to have to erase things and redraw them for that scenario where there might be a need for double bonds and so on. So using a pencil makes this way easier. You could use a pen, but it gets really messy. Okay, so those are the 2 key rules I want you to have in your Lewis structure when you've drawn it to see that it's correct. Does it have the right number? Do you have the right number of electrons? Does every atom have 8 electrons around it, meaning the octet rule? Okay. And do you have the right number of total valence electrons based on the formula of your molecule? Okay, so if you add up the number of valence electrons each of those individual atoms have, does that match the number of electrons in your picture? So let's talk about how to draw a Lewis structure with this method. By the way, those 2 rules are good enough for this class. There are other rules that come into play, especially if you go on to Chem 111, 112. I think the most important one is probably the concept of formal charges. So if you're curious about some of that, we'll talk about that. We can talk about that in office hours or outside of class. But basically, the third rule that we're not going to go into here is that when you draw a Lewis structure, you should minimize the number of formal charges. So if you're only taking Chem 103, just ignore that statement, because I think thinking about formal charges would definitely complicate this a little bit. But if you are going into Chem 111, 112, it isn't too bad, and I'd be willing to teach you about that. Okay, anyway, moving on. Let's talk about how to draw these Lewis structures. start off with your central atom. You look at your formula. Typically, your central atom is the first element that's listed, but if you have hydrogen as the first element listed, it's not going to be hydrogen. Hydrogen cannot be your central atom. Since hydrogen only wants 2 electrons to meet the duet rule to be like helium, it can only form a maximum of 1 bond. So it'd be really lousy as a central atom if it can only connect with one other atom. So hydrogen's always what we call a terminal atom. So if your formula starts with hydrogen, it's probably the second element that's listed. But otherwise, typically, the first element listed in your formula is usually your central atom. So start off by drawing that central atom, and then connect your other atoms to it with single bonds. So let's walk through a little brief example here so you can see how this comes into play. So if we have the formula NH3, we're going to start off with our nitrogen, and we're going to connect it with those 3 hydrogens with single bonds. Okay. Now, the next step is to add in lone pairs to make sure that all of your atoms are meeting their octet rule. Okay. In the case, of course, these hydrogens, they don't need any lone pairs. You should never put a lone pair on hydrogen. It follows a duet rule, right? It's trying to have only 2 electrons, and it meets those 2 electrons with its bond with nitrogen. So each of these hydrogens are happy. But now let's look at the nitrogen in question here. So our nitrogen has 2, 4, 6 electrons around, from its 3 single bonds with the hydrogens. So we have to give it a lone pair. Okay, that lone pair will be its 7th and 8th electron. 2, 4, 6, 8 electrons. Now, does this Lewis structure need any double bonds? Now, the short answer, of course, is that no, you can't form double bonds with hydrogen. But let's go back to the formula and see why not. Nitrogen is in group 15, which means a nitrogen atom by itself would have 5 electrons, or 5 valence electrons. Hydrogen's in group 1, so that means each hydrogen has 1 valence electron when it's a hydrogen atom. And since there are 3 hydrogens in our formula, NH3, 3 times 1 is 3. So the formula NH3 should represent 8 electrons. 5 valence electrons from the nitrogen and 3 from our 3 hydrogens. Does our Lewis structure have 8 electrons? Well, as we counted earlier, 2, 4, 6, 8. There are 8 electrons here, so this is a good Lewis structure. Okay, and we can stop there. All right, now this was a very simple example, so we're going to try something similar that involves a few more electrons. Quick note about counting electrons before we move on while we've got a simple example here in front of us. I don't know if you've noticed that I started counting in even numbers. Remember, in all of our diagrams, our electrons are paired up. They're either pairs of electrons in a chemical bond, so even though they're represented with one line, remember there's 2 electrons in here, or we have our lone pairs, which again always exist in pairs like this. Okay, now that's again as far as this class is concerned. It is possible to get molecules that have unpaired electrons, so it's not really a lone pair but just a lone electron. Those are what we call radicals. We're not going to deal with radicals in this class. That's an advanced topic that is not covered in Chem 103. So you will not get a question that involves radicals. So if you ever find that when you're totaling up your electrons and you wind up with an odd number instead of even, that might be a hint that you did something wrong and you might want to double check your math. Okay, so every problem you get in this course should have an even number of electrons. So that's why counting them becomes pretty easy. You just count them, 2, 4, 6, 8, numbers like that. I find that it helps to imagine a square around your atom. So if you were looking at, this nitrogen, and you imagined a square around it, there's something on all 4 sides of the square. So that will tell you that it's meeting its octet rule. 2, 4, 6, 8 electrons around that nitrogen. Okay, so let's try another example that's a little bit tougher. So let's say we're trying to draw NF3, nitrogen trifluoride. So we start off with our nitrogen in the middle, that's our central atom. And again, we're going to connect our other atoms, in this case 3 fluorines, with single bonds. Now, remember, our next step is to make sure that everything's meeting the octet rule. So, does this fluorine have 8 electrons around it? Well, it has 2 electrons from this bond, so we need to give it 6 more electrons to help it meet the octet rule. So we put in dots like this. Please don't mind my great MS Paint skills here. But 2, 4, 6, 8. That fluorine has 8 electrons here around it. So it's happy. It's meeting the octet rule. Okay. Likewise, you can do that for all the fluorines. Give this fluorine 3 lone pairs. 2, 4, 6, 8. That's 8 electrons around that fluorine. Oops. So that's happy. Same with this one. 2, 4, 6, 8. That fluorine has 8 electrons, so it's happy. Now, don't forget the nitrogen. That nitrogen also needs a lone pair to meet the octet rule. 2, 4, 6. So it needs that lone pair to give it 8. But now it has 8 electrons around it, and it's happy. Okay. Please note, by the way, since covalent bonds are shared between atoms, you can count them as 2 electrons for either atom, well, for both atoms that they're being shared by. Okay, so when I count the 8 electrons around this fluorine, I'm counting that bond, 2, 4, 6, 8. When I count the electrons around that nitrogen, I'm also counting that bond towards nitrogen because it's being shared, 2, 4, 6, 8. However, when I want to count the total number of electrons for this whole molecule, I only count these bonds once because, I'm not taking into account an individual atom's octet electrons, but I'm counting the total number of just electrons physically present in my picture. So, how many electrons should NF3 have? Well, again, nitrogen's in group 15, so there's 5 valence electrons. Fluorine is in group 17. Okay, so remember, that's 7 valence electrons that a fluorine has. Okay, if you need a refresher on that, we talk about this back in the previous chapter. Okay, so it's these 7 valence electrons that causes fluorine to form a -1 ion when it does ionic bonding. But over here, those 7 valence electrons are what they bring to the table when forming this molecule, and we need to represent, make sure our Lewis structure correctly represents this. Now, there are 3 fluorines, so 3 times 7 is 21. So we have 5 valence electrons from our nitrogen, we have 21 valence electrons from our fluorines, so that gives us 26 electrons in total. Does our diagram have 26 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. This diagram has 26 electrons, so we don't need to draw any double bonds here. This has the right number of electrons, and we can stop here because we've met the 2 requirements for a good Lewis structure. All of our atoms are meeting the octet rule, and we have the right number of electrons, in this case 26. Okay, let's look at some scenarios where we don't get the right number of electrons. Let's try drawing carbon dioxide. So feel free to pause here and try this out. So your carbon goes in the middle. You're going to connect 2 oxygens. Connect 1 oxygen with a single bond to one side of your carbon, and then connect the second oxygen to the other side of the carbon with another single bond. Now, when you give this molecule its lone pairs to make sure these atoms are meeting the octet rule, you'll probably notice you have too many electrons. Okay, so go ahead and try this out, so feel free to pause this here. But if you've joined us again, you should have drawn something that looks like this. You start off with a carbon in the middle, okay, and you connect an oxygen to either side, and you say to yourself, okay, this oxygen has 2 electrons here, 4, 6, 8. If I give it these lone pairs, now it's meeting the octet rule. Likewise, this carbon has 2 and 4 electrons here. Now it has 6. Now it has 8. It's meeting the octet rule. And of course, with this oxygen, I can treat it the same way as that other one. 2, 4, 6, 8. Now, the problem here with this molecule, and why this is not the final answer, and why this is not drawn correctly, is if you add up the total number of electrons, you'll notice that you have an issue here. You have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But the problem is carbon dioxide should not have 20 electrons. Carbon dioxide, or the carbon in carbon dioxide, being in group 14, has 4 valence electrons. Each of your oxygens, being in group 16, has 6 valence electrons. So 2 times 6 is 12. Well, instead of 20 electrons, this formula says that we should have 16, okay, not 20. So this can't be right. So to fix this, we're going to put in some double bonds. Now to do this, you're going to use your eraser, okay, and you are going to erase electrons around 2 atoms. So pick 2 atoms that are bonded to each other. So let's say we pick the carbon over here and this oxygen on the left. So if I'm picking these two, I'm going to erase a lone pair from my oxygen. I don't have an eraser that'll work here, so I'm just going to scratch this out. But if you were drawing this in pencil, you'd use an eraser here. And likewise for this carbon, I'm also going to pick a lone pair and erase it as well. Now, I can't just erase electrons and leave it like that, because now these atoms aren't meeting the octet rule anymore. So what I'm going to do is for these same 2 atoms that I selected, I'm going to draw another bond between them. And that's how we got this drawing over here. Now, I don't know if you noticed this, but I essentially erased 4 electrons and put 2 back. So if we count our electrons again, 2, 4, 6, 8, this oxygen's still happy. 2, 4, 6, 8, this carbon's still happy. But when we count the total number, 2, 4, 6, 8, 10, 12, 14, 16, 18, we have 18 electrons. Okay, so better than 20, but still not 16. So we probably have to do this one more time. So again, we'll pick 2 atoms that are connected to each other. So let's pick the carbon and the other oxygen. We'll remove a lone pair from the carbon, remove a lone pair from the oxygen, and draw another bond between them. And that's how we get this molecule here. Okay. Now, again, is this molecule meeting those 2 requirements? Are all my atoms meeting the octet rule? Well, hopefully they should be, because that's why we took care of that first. But 2, 4, 6, 8, that oxygen's good. 2, 4, 6, 8, that oxygen's good. 2, 4, 6, 8, that carbon's good. So we're all meeting the octet rule. So that's good regarding that one rule. But do we have the right number of electrons? Do we have 16 electrons in this diagram that we've drawn? 2, 4, 6, 8, 10, 12, 14, 16. We have 16 electrons, and therefore we've now met the second rule, and this is the correct Lewis structure for carbon dioxide. So, why don't we try practicing this? Okay, we're going to try drawing some Lewis structures. Now, in this, we have a couple of examples of polyatomic ions. So these are covalent molecules that happen to have a charge. How does that charge affect our drawing, our Lewis structure? The charge changes your total number of electrons when you're totaling that up. If you see a positive charge, that means you have an electron missing. Okay, so your total will be 1 lower than you would expect. Likewise, if you see negative charges, that means you have extra electrons, and you should add that number to your total. Okay, I'm going to go walk through the first 2 as examples for you. Or of course, you're always welcome to pause this video if you want to try it on your own. But I'll walk through the first 2, and then I'll have you, I'll leave the latter 2 as kind of just practice problems for you. Okay? So let's start off with NH4+, the ammonium ion. When we look at that, we start off with our nitrogen in the middle, and our 4 hydrogens are connected around it with single bonds. 1, 2, 3, 4. There's our 4 bonds. Now, if we want to check the total number of electrons here, our nitrogen has 5 valence electrons, because it's in group 15. Each of our hydrogens has 1 valence electron, but there's 4 of them, so I'm going to multiply that by 4. Okay. Oops, I'll draw that a little clearer. There we go. Okay, so 1 times 4. And now don't forget this positive charge here. That positive charge tells us that we're missing an electron, so we're going to subtract 1 electron from that total. So 5 plus 4 times 1, which is 4, that's 9. 9 minus 1 is equal to 8 electrons. Okay? So does this molecule have 8 electrons? Well, 2, 4, 6, 8, that nitrogen is immediately octetual, and since those are the only electrons shown in the diagram, that's the 8 electrons, this is a good Lewis structure. Now, the only thing that's left here is that we want to show that this molecule has the positive charge that we see in the formula over there. That needs to be represented in our molecule, in our Lewis structure. Now, again, we're not going to go into formal charges. If we did, you would figure out that that positive charge is actually on the nitrogen, and we'd put a little plus sign next to the nitrogen to show that. But in this class, all you have to do is put square brackets around your molecule and just show the charge on the outside. That just means that there's a positive charge somewhere in this molecule. Okay, so even though it is technically on that nitrogen, you don't need to know that for this class. We'll keep things simple and just put that positive charge outside in square brackets. Okay, and of course this only applies to ions. If you have a neutral molecule, you don't need to do this. All right, so let's try sulfate. Sulfate's SO4 with a 2 minus charge. Okay, so again, we'll start off with the sulfur in the middle with 4 oxygens connected to it. Okay, so we start off with those 4 oxygens. Okay, now again, the first thing you want to do is make sure that you're meeting the octetual. That's the first rule we're going to check. Our sulfur is happy, by the way, here. It's got 2, 4, 6, 8. That sulfur's got 8 electrons around it. It's good. But what about our oxygens? Oxygen, if we look at this oxygen on the left, it's got 2 electrons from this bond, but it needs 8. So we're going to meet the octetual by adding in 3 lone pairs to that oxygen. Okay, and in fact, we're going to do that to all the oxygens. There we go. Now you can see that they all meet the octetual. Okay, so 2, 4, 6, 8, that oxygen's happy. Okay, and all of them are happy that way. But let's make sure we don't need any double bonds or anything. So sulfur is in group 16. It has 6 valence electrons. Oxygen is also in group 16. So oxygen has 6 valence electrons. Though keep in mind there's 4 oxygens here. So 4 times 6, well, think about what that is. It's 24, right? So 24 and 6, that's 30 electrons. But don't forget the charge. This has a 2 minus charge. Now, that negative sign tells you that you've got extra electrons. And the fact that it's 2 negative means that you've got to add 2 electrons to your total. So instead of 30 electrons, we have 32 that should be in our diagram. Does our diagram have 32 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We have 32 electrons in this diagram. So I've drawn this Lewis structure correctly as far as Chem 103 goes. Again, we want to show that there's a 2 minus charge on this molecule, so we're going to put our square brackets around it and a 2 minus outside. Okay, though again, the way this is drawn, if we were doing formal charges, what you'd notice with the way this is drawn is that each of these oxygens has a -1 formal charge, and the sulfur winds up having a +2 formal charge. So when you add up everything, it comes out to -2 overall. Again, that's something you don't have to worry about for this class. For those of you going on to Chem 111 and 112, though, I just wanted to point out that if you see sulfate drawn in that class, you'll probably see it drawn slightly different from this. That's because of that third rule that we're not covering, and that's minimizing formal charges. So there's actually a way to draw this slightly better. It winds up violating the octet rule in the sulfur, but as we're going to see in a little bit, sulfur is one of those exceptions that you can violate the octet rule on it, and it's okay. All right, but again, don't worry about that for this class. We're gonna, if you draw this Lewis structure for sulfate in this class, and you're meeting that octet rule and you're meeting the right number of electrons, you'll get full credit for drawing something like this, even though you would probably lose points for something like this in Chem 111. Okay, so go ahead and try drawing carbon monoxide. Okay, so feel free to pause if you need to. Okay, so hopefully when you're done, you'll probably notice that you're going to wind up needing a triple bond between your carbon and your oxygen. Okay, but again, you can check your work at the end to make sure this is a good Lewis structure. Is everything meeting the octet rule? Carbon's got 2, 4, 6, 8 electrons around it, so it's good. Oxygen's got 2, 4, 6, 8 electrons around it, so it's good. Okay, now carbon brings 4 valence electrons to the table. Oxygen brings 6, so the molecule should have 10 electrons in total, which it does. 2, 4, 6, 8, 10 in total. So, so this is a good Lewis structure, but you probably didn't draw this to begin with. You probably started off with a single bond, like I told you, and lone pairs, and you realize that you had too many electrons. So keep that in mind, that this is one of those examples, again, that you're going to need to, this is a good example to practice drawing multiple bonds. Okay, so when you draw it with your single bond to start off with, you're going to realize that it has too many electrons, and you need to, put in extra bonds for this to work. Okay. Yeah, so if you're having trouble seeing that, I guess I can work through it really quickly for anyone who tried this problem out and got stuck on it. So basically, you probably started off with a molecule that looks like this. Started off with the carbon and the oxygen single bonded, and so that carbon had 3 lone pairs, so 2, 4, 6, 8, and this oxygen also had 3 lone pairs, 2, 4, 6, 8, but you probably quickly realized that this whole molecule has 2, 4, 6, 8, 10, 12, 14 electrons, which is definitely over 10. So that means we need to draw some double bonds out. So we get rid of that lone pair and draw a bond. And of course, this still doesn't meet the right number of electrons. 2, 4, 6, 8, 10, 12. 12 is not 10, so we still have to keep going. So we'll remove another lone pair and draw another bond between those two atoms. And now 2, 4, 6, 8, 10. There's our 10 electrons. Okay. This last one's thiocyanate. I don't know if it's, depending on what you're using to watch this video, that negative sign might not be very clear, but that's a -1 sign for thiocyanate. Okay. There are multiple ways to draw thiocyanate. So it depends on the actual molecule in front of you. For this particular version, let's draw it with a carbon in the middle. So I know we normally say the sulfur should be your central atom. Let's draw this one with a carbon as our central atom. Okay, so start off with single bonds to your sulfur, between your carbon and your sulfur, and between your carbon and your nitrogen. Okay. When you're done, you'll probably get something that looks like this. So feel free to check your work. So this is the final answer for thiocyanate. Okay, so when you total up your electrons, sulfur, which is group 16, has 6 valence electrons. Carbon, which is in group 14, has 4 valence electrons. And nitrogen, which is in group 15, has 5 valence electrons. When you add that up, you get 15, but don't forget that negative charge. That negative charge means you add an electron. So there's actually 16 electrons in your diagram. So if you started off with single bonds, you probably quickly realize you have too many electrons, and you need to start making double bonds, which you wind up doing. It's actually a very similar process to that example problem we did with carbon dioxide. Okay, it's just that we have sulfur and nitrogen now instead of oxygens. Okay, and of course, don't forget to put that negative charge in square brackets outside your molecule like this. Okay. Quick note here about where to put double bonds. You probably noticed we had some choices over which atoms I wanted to pick for erasing lone pairs and putting in a double bond. Okay, like I sometimes had choices over which ones I picked to do that. and I chose one way, but I could have easily have chosen another. So for example, with carbon dioxide, I started off by adjusting the carbon with the oxygen on the left, but I could have easily chosen to start with the one on the right. Okay. In real life, it's not like one double bond forms on one side and another molecule forms on the other side, or anything like that. Okay. Instead, if you were to observe a molecule like that in real life, you'd notice all of the bonds are identical. They are sort of in between a single and a double bond. They have like some partial double bond character. Okay. For those of you curious about how we can do that, we can actually measure bond lengths using X-rays, using like what we call X-ray diffraction or X-ray crystallography. I can go into more detail on that if you're curious, but basically we can measure the length of these bonds, and double bonds are shorter than single bonds. So instead of seeing one short bond and one long bond, let's say, we would see two bonds that are equal in length, and they're sort of in between the length of a single bond and a double bond. Okay, so this phenomenon where a double bond is actually spread out over multiple atoms, this is known as resonance. Now, when we draw one Lewis structure, we're drawing what's called a resonance structure. In reality, the molecule is actually kind of an average of all possible resonance structures. That being said, it's easier sometimes to deal with individual resonance structures, so we draw Lewis structures as we normally do. Like, don't stress about that. I'm just pointing out that in real life, it might look different. The molecule looks slightly different because it's the average of all those molecules combined, all the resonance structures combined. So for you guys, what might be a useful thing to keep in mind here, when you are drawing your Lewis structure and you come to a decision about putting in a double bond, think about where you could have put that double bond. Where else could you have put that double bond? And keep that in mind. Keep in mind how many options you had, because that's the number of resonance structures that are possible. Okay, so that's something to keep in mind there. So let's try drawing a couple of resonance structures just so we can see this in practice. Try drawing nitrate. So nitrate is NO3, and that's a -1 charge. I don't know if that might be a little hard to see, but that's a -1 charge. Okay. When you get a chance, also try drawing ozone. Ozone has 3 oxygens connected in a row. Okay, so you have a central oxygen and then 2 oxygens, one to the left, one to the right. So you're going to see when you try drawing both these molecules out, you're going to have a double bond in there somewhere, and you're going to notice you're going to have options for where to put that double bond. So let's have a look at this. So let's say we're drawing nitrate. Now, you may have drawn a resonance structure of nitrate that looks like this. You may have chosen to remove your lone pair from your nitrogen, remove a lone pair from the oxygen on top here, and drawn that extra bond between them. Okay? But you could have equally realized, oh, I could have drawn that double bond between the nitrogen and the oxygen on the left, for example. Okay, why didn't I choose that? Or you could have chosen for the one on the right. Okay. So which of these Lewis structures is correct? Well, they're all correct. All 3 of these are resonance structures for our nitrate ion. So if we wanted to draw a Lewis structure for nitrate, any one of these would be correct. Okay, you don't have to necessarily draw all 3. That being said, you should recognize that there are 3 possibilities here. Here's ozone. Ozone, like I said, has 3 oxygens connected in a row. Now, why is this sort of bent instead of in a straight line? We'll get into that in a little bit when we start talking about Vesper theory and the shapes of molecules. So you probably quickly realize that you need to draw a double bond in this molecule. So you can choose between the oxygen on the left with your central oxygen, which is what they've done here, or you could have chosen the one on the right. Now, what's this molecule we have drawn all the way here? Well, this is what we call a hybrid molecule. So here we've drawn individual resonance structures. The hybrid kind of shows that average of all of them. So you can see here we've kind of got this dotted line going across both oxygen-oxygen bonds, and that's to show the partial double bond character that these resonance structures provide. Okay, so this kind of looks what the this kind of should remind you what the molecule looks like. If you were looking at it, just in nature. Okay, so that sort of dotted line kind of shows that these are both partially single, partially double bonds. A very common example that you might come across of something with resonance is benzene. So you might notice that benzene, which is a six-membered carbon ring, it's a hydrocarbon made up of carbons and hydrogens only. When you're going to have alternating double and single bonds, but due to resonance, where those double bonds are can differ. There's two different resonance structures here, right? So what does the hybrid of this look like? Well, oftentimes, if you're seeing benzene drawn, in organic shorthand, we don't bother writing C for carbon. It's understood that any bend in a line that's not labeled is a carbon. And likewise, we don't bother drawing in hydrogens. It's kind of understood there are enough hydrogens to make sure that the carbons are meeting the octet rule. So in organic shorthand, okay, or a bond line diagram, instead of drawing these individual Lewis structures, which you totally can, people do draw them, but the hybrid that you'll often see for benzene looks like this. It's a hexagon, and it has a ring in it to represent that these double bonds aren't stuck in the locations that are drawn in their Lewis structures. In reality, they're in both places at once. Okay, it's kind of like a like I said, a kind of a combination or an averaging of both of these resonance structures. Okay, I mentioned some exceptions to the octet rule. Well, here they are. So with boron and beryllium, okay, these are two small atoms, it's possible for them to go under the octet rule. A lot of boron compounds only have 6 electrons around the boron, which in turn yields to some really interesting chemistry. Like that shortage of electrons on boron really allows you to do some interesting reactions using boron as one of your reactants. Okay, or usually like a borane, which is a derivative of BH3, boron trihydride. But by the way, if you try drawing BH3, and I'll show it on the next slide, you count the electrons around the boron, that's where you'll see it only has 6 electrons. Okay, beryllium is another example where you might see this. Beryllium's a metal, technically, so when we talk about covalent molecules or Lewis structures involving beryllium, kind of take it with a pinch of salt. Because beryllium is such a tiny atom, a tiny metal atom, it sometimes behaves a little covalently. It behaves a little bit like a nonmetal because being that tiny, it's very electronegative, meaning it will suck electron density towards it. Okay, so again, be careful of the context here. Sometimes beryllium we'll use it in ionic compounds, but if you do see it in a covalent compound, just know that you'll only see 2 bonds coming off of it, meaning it only has 4 valence electrons in that structure. So watch out for that. Okay, that's normal, is what I'm getting at. Now, what about exceeding the octet rule, going over that limit of 8 electrons? Well, if you have an element that's in period 3 or below. Okay, now please note again, period 1 is hydrogen and helium, and then period 2 is lithium all the way to neon. Okay, anything below that, so period 3 and below, it's okay to exceed the octet rule if you have to. If you're curious about why this is the case, you're starting to get really close to the d orbitals at that point. Once you start getting to period 3 and below. So Now, these d orbitals are only slightly higher in energy. Like the energy gaps between orbitals start getting smaller once you start getting to bigger and bigger atoms. So it doesn't cost a lot of energy to dump those extra electrons into an empty d orbital, for example. Okay, um, so that's why basically, if you want the explanation for why it's possible, that's the reason. Okay, you can shuffle electrons a little bit easier in larger atoms. But that being said, the key thing here for you is to recognize you can exceed the octet rule for anything in period 3 and below. So for example, on a sulfur or phosphorus, we can have more than 4 bonds to those atoms because, again, exceeding the octet rule is allowed. Okay, so sulfur hexafluoride, SF6, and phosphorus pentafluoride, PF5, these are real molecules that exist. Okay, they're not particularly stable, but they do exist. And so if you try drawing them out, you're going to see some weirdness there. So first things first, here's our boron trihydride and our boron trifluoride. Again, notice in both cases, boron has 3 bonds and therefore 6 electrons around it. Okay, so 2, 4, 6 electrons around that boron, 2, 4, 6 electrons around that boron. With our sulfur hexafluoride and phosphorus pentafluoride, notice that the sulfur here has 6 bonds to it, to its, each of its 6 fluorines. So if you add that up, that's 12 electrons that's on your sulfur, which obviously, like, that's way more than 8. But that's okay. Again, sulfur is allowed to exceed the octet rule. So I've just spent some time talking about how to draw molecules. How do we represent molecules as pictures? But now let's talk about how to write out names and formulas for these molecules. So this is a very similar approach to what we saw in the last chapter, where we take our ionic compounds and we write out a formula using the symbols for the elements making up that compound and use subscripts to show their relationship to each other. And then we have names. We have a systematic way of naming these molecule, or well, in ionic compounds in the previous chapter, molecules in this chapter, and so that we can refer to these just by talking about them. So just like in the last chapter, we have a systematic way of writing out formulas and writing out names for these compounds. And again, the lab that we do this week should cover how, should give you lots of good practice at these rules that we're going to go over in a second. Okay, so when it comes to naming covalent compounds, you're going to see some parallels here to how we named simple ionic compounds. Namely, we say the name of our first element in our compound, followed by the name of the second element with its "ide" ending. Okay, now here's where things get a little bit different. Unlike ionic compounds, where you can figure out the numbers of your elements by balancing out charges, with covalent compounds, we don't have any charges to work with. So instead, we need more information in the name to tell us that relationship between our 2 elements making up our compound. And to do this, we use Greek prefixes. So you need to memorize these Greek prefixes because they will help you point out the number of atoms of a particular element in your formula. In other words, the subscript you'll see in the formula. Okay. Now, when it comes to memorizing these things, the nice thing here is that there are a lot of English words that use these Greek roots. So it might come in handy to think of English words that have them to help remind you of those words. Okay, so for example, the prefix for 1 is mono. So for example, think of a monocle, the thing that Mr. Peanut wears, right? Like it's just one eyeglass, or an eyeglass covering one eye. So mono means 1. Okay, di means 2. All right, be careful with Latin prefixes. I think a lot of people think, oh, bi means 2, but that's the Latin root. There's a lot of similarities between Greek and Latin, so you've got to watch out for confusion there. So di is the prefix for 2. Tri is the prefix for 3. I think that one's pretty straightforward. Think of a triangle or a tricycle, right? Tetra is an interesting one. Tetra means 4. Normally you I think a lot of people, while they probably aren't as familiar with that Greek word, there's a similar Russian word that you're probably familiar with, and that's the video game Tetris. Okay, that name Tetris in Russian means four. That's why a Tetris is when you clear four lines at once in the game. And I don't know if you've noticed this, but all of the blocks in Tetris are made up of four smaller blocks. And inevitably, that always blows someone's mind. It definitely blew my mind when I first noticed that. I'm like, huh, they are made up of four smaller blocks. And that's where the name comes from. So anyway, if you're trying to remember the Greek prefix for four, it's tetra, which is just the Greek equivalent of the Russian word Tetris. Okay. And once we get to five onwards, now we're starting to get into names that are very familiar to us if we've taken geometry at any point. So penta is the prefix for five. So think of a pentagon or a pentagram, which is a five-pointed star. Okay. Hexa is the Greek prefix for six. Okay, so think of a hexagon, of course. Hepta is seven. Now, again, this is one of those ones that you've got to watch out for with the Latin equivalent. A lot of people want to write down septa for seven, but hepta is that Greek is the Greek prefix that you have to use instead. Okay, yeah, I mean, I think most people probably think of septa, as like with September being the seventh month and October being the eighth month and November being the ninth month and December being the 10th month in the Latin calendar. I'm joking a little bit here. All the months were shifted by two when they added months for July for Julius Caesar and August for Augustus Caesar. But in case you're wondering why the number of the month and the name of the month doesn't match up in Latin, that's why. But hopefully that'll help you remember at least the Latin prefix. But once we get to 8 and 9 and 10, of course, 8 is octa. You can think of an octopus having 8 arms. Deca is the prefix for 10. Think of a decade, which is a period of 10 years. Okay, so beyond 10, I don't think you really need to memorize anything beyond that. They start to get a little bit repetitive after that. You can use prefixes to get to 11 and 12 and so on. But to be honest with you, in this class, you're probably not going to go beyond a subscript of 10. So, that's really all you've got to memorize. Now, how do we use these prefixes when writing out our names? Well, again, the key thing to realize is that with our ionic compounds, it's kind of silly to do this, right? And we don't see this because, for example, if we have BaCl2, that is barium chloride, using our ionic name. We don't say barium dichloride because that's kind of silly. The only combination of our barium ion with its 2+ charge and a chloride ion with its -1 charge has to be BaCl2. Right? There's no other barium chloride than BaCl2, so it's kind of silly to have that prefix di. Likewise, sodium sulfate is Na2SO4 because sodium has a +1 charge, sulfate has a 2- charge. Of course, you need two sodiums to balance that out. So writing disodium sulfate is kind of redundant when it comes to ionic compounds. But with our covalent compounds, we have lots of different combinations. Look at the combinations of nitrogen with oxygen. Okay, you don't know how they're going to combine because there are many different ways to do this. So we need different names to show which formula we're talking about. Okay, and this is where we're going to have our Greek prefixes. So look at this first example here on the left. We have one nitrogen and one oxygen. Okay, so we call that nitrogen monoxide. The mono here telling us that there's one oxygen. Okay. By the way, for the first element, if there's one of it, you don't have to say mono for it. It's understood that if there's one of it, if there's no prefix, there's one of that first element. So we just say nitrogen monoxide and not mononitrogen monoxide. Okay. Now look at the second example here. We have one nitrogen and two oxygens. Okay. So that is basically, we still say nitrogen to start off with, but the prefix for 2 is di, right? So it would be nitrogen dioxide. Now look at this third example here. Here we have two nitrogens and one oxygen. So the prefix for 2 is di, so we see dinitrogen monoxide because there's one oxygen. Okay, notice in all three cases we still have that "ide" ending for our oxide, so we still do that just like we do for our ionic compounds, like our barium chloride up here. The only difference, of course, though, is we have to use these Greek prefixes to state how many there are of each of our elements. Okay, the only exception being you don't have to use a prefix if there's one of that first element. You don't have to say mononitrogen. Okay, now I don't know if you guys noticed this with the oxide, but if you take that prefix mono, which ends with an O, and you have the "ide" ending of oxide, which or of oxygen, which is oxide, oxide starts with an O as well. Now, this can be kind of awkward when you say monooxide. So typically, when you have vowels together like this, like an A and an O or two O's, typically you drop the vowel in your Greek prefix. Okay, so for example, here we have dichlorine, and we have one oxygen, so that would be, instead of saying monooxide, because that's, again, kind of awkward to say, we drop an O and we just call it dichlorine monoxide. Okay, so we drop the O from the mono to make it mon oxide. Here's another example, tetraphosphorus, and we've got 6 oxygens, right? So 4 phosphoruses, which is tetraphosphorus, 6 oxygens, so 6 is hexa, but again, that A and that O, hexaoxide, it just sounds really awkward, right? So we take out the A and it just becomes tetraphosphorus hexoxide. Okay, so it's a little bit easier to pronounce. So just something to watch out for when it comes to naming these covalent compounds and using those Greek prefixes. Okay, so let's work through a couple of examples, and then you can try some of these out as practice problems as well. So in this first one, we have an iodine and 5 fluorines. So iodine, there's only one of it. So remember, if it's that first element, you don't have to say monoiodine. We can just say iodine. There are 5 fluorines. What's the prefix for 5? Well, it's penta, right? Think of a pentagon or a pentagram. So pentafluoride. Remember, we're going to use that "ide" ending for fluorine. So we take that first root, fluor, and add "ide" to the end of it. So iodine pentafluoride. Note that also, just like our ionic compounds, we have a space between that first word and that second word, between our first element and the second element. Okay, but there's no space between our prefix and our the name of our element. Okay, let's try this next one. There's 2 borons and 3 oxygens. So the prefix for 2 is di. Okay, so diboron. The prefix for 3 is tri. And we take oxygen, take that first syllable ox, and add "ide" to it. So it becomes diboron trioxide. Okay, so again, notice the sort of that pattern there. Okay, our number becomes the prefix for this element. Then we take the name of that first element. Our number over here becomes the prefix for our second element, and we take the root of that second element and add "ide" to it. Okay. This third one here is NO3. Now, you might be tempted to call this nitrate. Remember, nitrate's a polyatomic ion with a negative charge. So this is technically not nitrate because it's neutral. Okay, so go ahead and use your typical covalent rules to name this. Okay, so hopefully you should have gotten nitrogen trioxide. There's 1 nitrogen, so you don't need a prefix for it. And there's 3 oxygens, so it becomes trioxide. Okay, so here's some more examples. Feel free to pause this video and try these out, and then I'll put up the answers so you can check your work. Okay, so we have 1 arsenic and 3 chlorines, so it's arsenic trichloride. We have 1 carbon and 2 oxygens, so that's carbon dioxide. And we have 1 carbon and 1 oxygen, so carbon monoxide. Note that, again, that if you have 1 of the first element, you don't need a prefix for it, but if you have 1 of the second element, you should add that prefix mono. Okay? Okay. So going from names to formulas and formulas to names for covalent compounds is much simpler than we saw with ionic compounds, because while the naming conventions are pretty straightforward for ionic compounds, you do have to balance those charges, and that takes a little bit of work sometimes. In the case of covalent compounds, the numbers are right there in the name for you. So that takes a lot of the work out of it. Now, in the lab that we do, we have everything broken down into tables so that you get to practice one particular rule at a time. However, on a quiz or exam, and in real life in general, you're not immediately told what type of compound you're dealing with. So before you try to apply rules, you want to first figure out which rules do you need to apply. Okay, so you want to look at your compound and ask yourself, what elements are making this up? Okay, that's your first step when it comes to doing a problem that involves nomenclature, that involves writing out a name for a compound. Okay, so you look at your formula, you look at the symbols making up your formula, and ask yourself, okay, what are these elements? Okay, so you look at your first element and ask yourself, is this a metal or a non-metal? Okay, now occasionally you might have ammonium, which is a positive polyatomic ion, so it might be good to start recognizing NH4 as ammonium, okay, if you haven't already memorized that yet. But my point here is that as soon as you see that first element is a metal or ammonium, you automatically know that you're dealing with an ionic compound. Okay, and then immediately you can start using, you start going into your ionic rules. You can ignore your covalent rules. You know that your ionic compound's not going to have a Greek prefix in it, so you can immediately rule out those answers on a multiple choice quiz. Okay, so again, you want to write out the name of your metal, but this involves an extra step of noticing what type of metal you have. If your metal is in group 1 or 2, or if it's aluminium, zinc, or silver, it only forms one type of positive ion, so you just say the name of that metal. However, if it's any other metal, you're going to need a Roman numeral because you can have more than one type of that type of metal. Okay, and so your name should reflect what type it is. And so you need to figure out the charge on that metal and write it out as a Roman numeral in your name, okay, using the stock system. Okay, again, go back to the previous chapter's video if you want to see some more practice with this. And of course, all of section C of your lab report also gets you to practice this concept. Okay. The nonmetal, of course, is just, if it's just one nonmetal, you just add that "ide" ending to it. If it's a polyatomic ion, then you simply just say the name of the polyatomic ion. Again, really straightforward, but you just have to recognize this in your formula. Okay, so you recognize that you have a polyatomic ion because there's more than one nonmetal present. Okay, now if your compound has only nonmetals in it, okay, if it has two nonmetals, then it's going to be covalent, and then you just apply the rules that we just learned. You say the name of your first element and the name of your second element with its "ide" ending, but use a Greek prefix before each to say how many there are of those elements. Okay, but that first step is really important. Looking at your compound and identifying what type of compound it is. If you can get into that habit of checking yourself before trying to apply rules immediately, first determining what type of compound am I dealing with, so then you can figure out which rules you need to apply. That'll save you a lot of grief on quiz problems involving nomenclature. Okay, let's talk a little bit about acids. Now, acids are technically covalent compounds. They're made up of nonmetals. However, they're interesting in that they behave ionically when they dissolve in water. They split up into a hydrogen ion, okay, and this is kind of what makes them act as acids. We'll spend an entire chapter talking about how acids work towards the end of this semester. But for now, let's just try and figure out how they're named, just because we're going to come across them quite a bit in our labs. So it's probably going to be useful to be able to identify them. Okay. Now we have two main categories of acids we're going to deal with here. We have what are called binary acids, where you have a hydrogen ion paired up with one nonmetal anion. Okay, so one negative nonmetal ion. And then we have what are called oxyacids, where we have a polyatomic ion, so it's usually something containing oxygen, okay, like nitrate or sulfate or any one of those. and it's again paired up with our H plus ion. So let's look at the naming conventions for both of these. When it comes to binary acids, you always start off with the prefix hydro and the suffix ic acid. All right, now what goes in between those two is derived from the root of our non-hydrogen element. So whatever your anion is from your binary acid, we take that root word and that goes into the name. So look at HCl, all right? That's made up of H plus and Cl minus. Okay? So Cl is chlorine, right? So we take that root word chlor and we add the prefix hydro and the suffix ic acid to it. So it becomes hydrochloric acid. Okay, notice that there's no space between hydro and chloric. Okay, it's just one word, hydrochloric. There's a space before the word acid, though. Okay, let's try another example. Here we have HI. So look at iodine, that's what I is, and take that first syllable, iod. So it becomes hydroiodic acid. Okay, and you can do this with any binary acid. If you had HBr, Br is bromine. What's that first syllable there? Brome. That becomes hydrobromic acid, and so on. Now, with oxyacids, you need to look at the name of the polyatomic ion that's making up your acid. Essentially, whatever your negative charge is on your polyatomic ion, you have that many H pluses balancing it out, right? So getting the formula of an oxyacid is pretty straightforward if you've memorized your polyatomic ions, okay? And even if you haven't, just looking them up, you should be able to figure out how many hydrogens you'd need for each one. But when it comes to naming them, you take the name of your polyatomic ion. If it ends with an ate suffix, the acid will end with ic acid. No hydro here, unlike a binary acid. You just say that root word of your polyatomic ion followed by ic acid. Now, if your polyatomic ion ends with ite, the corresponding acid ends with us acid. Okay, so here are examples. So here we have H2SO4. SO4 2 minus, remember, is sulfate. So H2SO4 is sulfuric acid. All right. Likewise, H2SO3 is called sulfurous acid because SO3 2 minus is the sulfite ion. Okay. You can see this also with nitrate and nitrite. HNO3 is called nitric acid because NO3 minus is nitrate. Okay, so see that relationship between ate and ic acid. And likewise, NO2 minus is nitrite, so HNO2 is nitrous acid. Okay, so if your polyatomic ion ends with ate, the corresponding acid will end with ic acid. If your polyatomic ion ends with ite, this corresponding acid will end with us acid. Okay, there's sometimes a few slight differences in that root word, but I think sulfate and sulfuric acid is one of those exceptions. I think phosphate and phosphoric acid is another example. But in the case of nitric acid, there really is no difference. That niter prefix is still the same in nitric acid and nitrate. Okay. So now that we've talked about naming covalent compounds and we've talked about drawing them, let's go back to our drawings and see what they look like in real life. Okay, I've kind of talked a little bit about how these molecules should match up in their in meeting the octet rule around your atoms and having the total number of electrons correctly. But we haven't really talked much about the shapes of the molecules. And that's something we need to look at because the shapes of these molecules does determine a lot of their interesting physical properties that we're going to end this chapter with. All right. So before we get to that, we first need to talk about the shapes of molecules. And this is where we run into a problem. When it comes to try to draw a molecule, we are forced to draw it on paper, or in this case, I'm representing it on a screen, but these are two-dimensional, right? Your paper or screen or whatever you're using is a two-dimensional surface, And therefore, you're going to run into problems when you're trying to represent a three-dimensional molecule. So for example, here I've got methane, right, which is CH4. We've got a carbon in the middle, okay, and four hydrogens connected to it, okay. So with this molecule, if I asked you what is that bond angle between these two carbon hydrogen bonds, if you look at this, you would say, oh, that's 90 degrees, right? It looks like 90 degrees. But there's a lot of empty space that's on, if you're looking at this, if this was drawn on a piece of paper, there's a lot of empty space above the paper and behind the paper, right? That we're not really using. A lot of three-dimensional space here. So does this molecule look like this in 3 dimensions? And the answer is no. Okay, we draw it this way in paper, but this is not what it looks like in real life. This bond angle actually isn't 90 degrees in real life. Okay, these four hydrogens are not crammed around the carbon this way. So to understand what shapes molecules actually take in real life, we use what's called VSEPR theory. That stands for valence shell electron pair repulsion. The convention is to pronounce it VSEPR. I'm not sure why people don't pronounce it VSEPR, but anywho, it's VSEPR theory. And what does that mean, valence shell electron pair repulsion? Well, when you look at the central atom of your molecules, you've got pairs of electrons around it, whether those pairs are from bonds with other atoms or if they're lone pairs. Now, electrons are negatively charged, and things that have same charge will repel each other. So these bonds and lone pairs and things repel each other, and it's this repulsion which dictates the shape of our molecules. Okay, that's basically what VSEPR theory means. The best way to explain why molecules take the shapes that they do, according to VSEPR theory, is perhaps with balloons. So we're going to start off with the simplest structure that we can, and that is this linear shape. So if you have your central atom and you have two atoms coming off of it, they want to get as far away from each other as possible. Okay, so balloons explain this a little bit easier because they just naturally fill up space. So you can't have them occupy the same space as you try to push them together like that. So in the case of a linear molecule, the angle formed by the two atoms connected to your central atom is 180 degrees, all right? Because anything less than that, and the balloons start pushing against each other. And so this is where they are furthest apart, when they are in a straight line, which is where we get the name linear. So let us see what happens when we add a third balloon to this. Okay. Try and get my balloons to look about the same size. All right, so let's add our third balloon to this molecule. And here we have a trigonal planar molecule. So as you can see here, the three atoms form a triangle, and if you look from this angle, they are completely flat. Okay, so that's why it has the name trigonal planar. That brings us to the earlier molecule that we started this section with methane. We have our carbon in the middle and four hydrogens. What does that molecule look like? All right. So if our molecule were confined to 2 dimensions, where all 4 of our atoms had to be flat, they had to be in the same plane, this is what it kind of looks like. Right? We have our 4 atoms kind of in the same plane forming this sort of cross pattern, or X, depending on how you look at it. The problem with this, of course, is if you look at this, you've got all this wasted space on either side of this molecule. Okay, the front and the back of it, if you will, looking at it from this angle. So, this is where we take advantage of 3 dimensions. If I can push two of these one way and two of them the other, here we have our tetrahedral molecule. Okay, so notice that this is taking up 3 dimensions of space, and we no longer have our atoms crammed together at 90 degrees like they were when this molecule was forced to be flat. But by taking advantage of 3 dimensions, this is what a tetrahedron looks like. I'm just going to play with these for a while. Just, give you an idea of what this looks like in 3 dimensions. This is way more fun than it should be. So when we connect the four surrounding atoms around our central atom, we get a 4-faced pyramid, which is called a tetrahedron, right? Tetrahedron means, well, tetra and hedra means 4 faces. So that's where we get the shape tetrahedral. Okay, so again, notice how that bond angle improves when we take advantage of this molecule in 3 dimensions. Okay, instead of being crammed at 90 degrees, the bond angle instead opens up to 109 degrees or so. So you're gaining almost like 20 degrees of extra space there just by taking advantage of all 3 dimensions of space. Quick note here about the notation we've got. This is one way of representing a 2-dimensional or 3-dimensional molecule on 2-dimensional paper. This solid wedge tells you that this hydrogen is pointing towards you, and this dashed wedge means that this hydrogen is pointing away from you. Don't stress too much about using this kind of notation. Basically, when it comes to drawing Lewis structures, if you want to draw them like this, where it's, again, confined to a 2-dimensional sheet of paper, that's totally okay. Okay, as long as your Lewis structure has the, has things meeting the octet rule, it has the right number of electrons, I'd still mark it correct. You just have to recognize that this shape is tetrahedral. Okay, and so we're going to look at how to figure that out just by looking at these molecules, these Lewis structures, how to determine what that shape is. Now, there are greater forms of, just greater forms of symmetry, greater names, Vesper shapes that involve more atoms around your central atom, as we saw in the case of phosphorus pentachloride and sulfur hexafluoride, where you can exceed the octet rule. To be honest with you, you don't really need to know these. I put these in here because I think they're interesting, and for any of you going on to Chem 111 and 112, you would need to know these. But for Chem 103, you can stop at tetrahedral. All right. Now, you've probably noticed all of the examples that we looked at involved molecules where we had only atoms around our central atom. Okay, so what about molecules that have lone pairs on that central atom? What do we call those shapes? Because we can't just use the same names that we had earlier. So let's have a look at a water molecule here. Now, when you draw water, you draw oxygen in the middle, you have single bonds to your 2 hydrogens, and your oxygen has 2 lone pairs to meet the octet rule. Okay, so now most people, I think, would draw water to look like this. Okay, it's a very symmetrical appearance where we've got our hydrogen on either side and our 2 lone pairs. Now, I'm going to ask you a question. What is that bond angle between those 2 hydrogens? Just looking at the way this picture is drawn, you might be tempted to say, oh, that hydrogen, oxygen, and hydrogen are in a straight line. This is linear. That must be 180 degrees, right? If I get out a protractor and measure this seems like 180 degrees. But the problem here is that you're not thinking 3-dimensionally. This is what it looks like when you draw it on a flat piece of paper, but this is not what a water molecule looks like in real life. Okay? You have to remember that those lone pairs are pushing on those 2 hydrogens, those bonds with hydrogen. So if we count the total number of electron pairs, okay, the number of electron groups here, we have 2 bonds and 2 lone pairs, that's 4 things in total. Okay? So in other words, that bond angle is going to be very similar to that of methane, where it's about 109 degrees. Okay? Those lone pairs are actually pushing those 2 hydrogens closer to each other. Okay? And so we have what's called a bent shape. For those of you who've seen my video on the lab, you probably noticed that I prefer to draw my water molecules bent like this. Again, just to remind me of what its shape actually looks like in 3 dimensions. Okay, so if you want to see what it looks like 3-dimensionally, again, this is kind of what we have going on. We still have that approximately 109-degree bond angle that we see in methane. Okay, all we've done is we've swapped out these 2 hydrogens for 2 lone pairs. Okay, but the repulsion is more or less the same. All right, actually probably a little bit more. Lone pairs, because they don't have any atoms nearby to sort of shield that negative charge, that repulsion's a little bit greater, which kind of squeezes these hydrogens a little bit closer to each other. But again, we're talking about roughly 109 degrees, somewhere in that ballpark. Okay, but my point here is again that these 2 bonds are not at 180 degrees. This is not going to be linear because of these lone pairs. These lone pairs are going to push these atoms closer together, bending the molecule. So that's something to keep in mind when it comes to the shapes of molecules that have lone pairs on that central atom. You want to also consider what that repulsion with those lone pairs is going to do. So let's look at all the different scenarios of molecules that you might come across. So we've already seen trigonal planar. So if we have 3 electron groups around our central atom, we have a trigonal planar molecule. But if we swap out one of those for a lone pair, that lone pair is going to push those 2 atoms closer together. So we again have that similar 120-degree bond angle. We call this shape bent, okay, because those 2 atoms are bent towards each other. Likewise, we've already seen that if we have 2 hydrogens, 2 atoms and 2 lone pairs, that's also bent. Okay. But another scenario you haven't seen before is what we call trigonal pyramidal. So if we have 3 atoms and a lone pair, okay, that lone pair pushes these 3 atoms downwards to make that pyramid shape, a 3-sided pyramid, hence the name trigonal pyramidal. Okay. Again, here are some examples of 5 and 6 electron pairs. You can ignore them. We're not going to deal with that in this class. I again just put this extra information for anyone who finds it interesting or is moving on to Chem 111 and 112. So, how do we remember the different names and how do we link them to our Lewis structures? There's 2 ways you can do this. I've got 2 tables set up here. This second table is kind of the same way it's set up in your lab manual, where you look at total number of electron groups and decide how many of them belong to atoms and how many belong to lone pairs. Okay, so for example, here we have both of these have 3 electron groups. Okay, 3 plus 0 or 2 plus 1, and these last 3 involve 4 electron groups. Okay, and this is kind of the same setup as your lab manual, where you look at total number of electron groups. However, one thing I find personally easier to remember this, or to try and like figure out our shape of our molecules, is to kind of ask ourselves 2 questions. First, ask ourselves how many atoms are attached to our central atom, and then ask ourselves, does it have lone pairs or not? Okay, so even the number of lone pairs isn't important. Does that central atom have lone pairs? Yes or no? Okay, because that'll help us group these together. Okay, so basically, if you consider this as kind of a checklist, all right, so if we look at number of atoms, question mark, and lone pairs, okay, yes or no? If we have 2 atoms, we have 2 atoms coming off our central atom, I should say. This is point out, this is atoms attached to our central atom. Okay. If there's only 1 atom attached to our central atom, then it's obviously linear because bonds are linear. But if we have more than 1 atom, then we've got to ask ourselves these questions. So if we have 2 atoms attached to our central atom, again, we ask ourselves, does it have lone pairs or does it not have lone pairs? So no lone pairs or yes lone pairs. If it's 2 atoms with no lone pairs on that central atom, those 2 atoms want to get as far away from each other as possible, and that shape is linear. Okay, that's why we have that shape linear. As soon as you have lone pairs on the central atom, that lone pair or lone pairs is going to push those 2 atoms closer to each other, thereby bending the molecule. Okay, so that's why both of these bent shapes here, it doesn't matter whether you have one or two lone pairs, we still have a bent shape for that molecule. Okay, so as soon as you have like one or two lone pairs, those two atoms are going to be pushed towards each other, bending that molecule. Okay, now what if you have three atoms attached to a lone pair, attached to your central atom? Sorry. Well, again, if you have three atoms, those three atoms are going to form a triangle. So we're going to get trigonal something. This is going to be trigonal something. The question is, what is that second word that follows it? Well, if there are no lone pairs, those three atoms want to spread out as far as possible, and to do that, they make the molecule flat. Okay, so it's going to be trigonal planar if there are no lone pairs. However, as soon as you put a lone pair on that central atom, those other three atoms are pushed downwards away from it, turning it into a pyramid shape. Okay, so notice that, again, we have trigonal corresponding to the three atoms attached to our central atom. Whether the number of lone pairs determines whether it's going to be flat or pyramid shaped. And then finally, if we have four atoms connected to our central atom, that's going to be tetrahedral. Just think tetra is four. Okay, we're not going to go to any examples that exceed the octet rule here when it comes to these shapes as far as Chem 103 goes. So you can assume that pretty much every atom, every molecule that you see that has four atoms connected to your central atom is not going to have any lone pairs, and therefore is going to be tetrahedral. Okay, so again, just link up four atoms connected to your central atom. That four is tetrahedral. Okay, so once we look at the shapes of molecules, okay, and we start thinking about how the electron density of molecules is focused, we can start looking at the polarity of molecules. This is going to be kind of important when we start looking at intermolecular forces, which will be the topic that kind of ends this chapter. Okay, so in order to get into that discussion, we first want to talk about the polarity of the bonds within our molecules, as well as the polarity of the molecules as a whole. Now, to understand polarity of bonds, we first have to look at electronegativity. Electronegativity maybe rings a bell for you, but back in chapter 3, when we looked at periodic trends, I mentioned that there were three main trends we could get from our periodic table. And back in chapter 3, I talked about two of them. I mentioned that we can look at atomic radius, or the size of atoms. Atoms generally get bigger as you move down into the left of your periodic table. Or we could look at ionization energy, our first ionization energy. This typically increases as your atoms get smaller. So in other words, as you move to the top and right of your periodic table, your atoms are getting smaller, and therefore you'll have higher first ionization energies. Okay. Well, the third property, or third periodic trend, which I said I would get to in this chapter, is electronegativity. Electronegativity is the tendency of an atom to want to pull electron density from neighboring atoms towards it. Okay, so it's how much does an atom want electrons? It's a way of sort of quantifying that. Now, electronegativity follows the same trend as ionization energy in that atoms typically get more electronegative as you go to the top right of your periodic table. Now, the only difference here is that the noble gases are treated as not having any electronegativity. The reason for this is that we measure electronegativity by looking at compounds, looking at the bonds that these atoms formed, and since noble gases don't really form bonds, we kind of ignore them when it comes to electronegativity. So the most electronegative atom is the top rightmost element that is not a noble gas, and that is fluorine. So fluorine, all the way towards the top right of group 17, is your most electronegative element. And if you go in the opposite direction, francium, in the bottom left, is the least electronegative. Okay, so typically atoms get more electronegative as you move to the top right of your periodic table, and get less electronegative as you move to the bottom left. Okay, So this explains a lot of why we see the bonding that we do between metals and nonmetals and between nonmetals in covalent bonding. Okay, uh, you could describe bonding as kind of like a tug of war, where the rope is the electrons involved. Okay, so nonmetals with their very low electronegativity are kind of like someone who isn't really pulling on the rope. Okay, so when a metal and a nonmetal are playing tug of war, the nonmetal really wants those electrons. Okay, that's kind of why nonmetals to the top right of your periodic table have really high electronegativities. They really want to pull electrons towards them. So if a metal and a nonmetal are playing tug of war for those electrons, the nonmetal is really pulling on those electrons, and the metal doesn't really care. It's just like, okay, whatever, take your stupid rope, right? That's basically ionic bonding in a nutshell. It just the metal gives those electrons to the nonmetal, and the nonmetal takes them. Okay. Now, what about covalent bonding? Well, in covalent bonding, you've got two nonmetals. They both want those electrons. So it's like two people really trying to win tug of war. Now, what we're going to get into here is the distinction between a polar covalent bond and a nonpolar covalent bond. Okay, so when we look at the electronegativity values here, okay, I pointed out that they typically increase to the top and right. So if we compare the two elements in our covalent bond and ask ourselves, who would win this tug of war? Which of these elements has a higher electronegativity and therefore is stronger? That goes a long ways to understanding the type of covalent bond we're looking at. Are those electrons shared equally is basically the nuance we're adding to this. Okay, so covalent bond involves a sharing of electrons. Again, all covalent bonds involve that. The question is, are we sharing those electrons equally? All right, so basically it comes down to that tug of war analogy I just had, right? So let's say we had two oxygens that were sharing electrons. Okay, so we have, let's say, our oxygen atom here, and it's bonded to another oxygen atom. So here's the Lewis structure of oxygen, of O2. All right, there's going to be a double bond between the two oxygens. I'm not going into the whole like what led me to drawing it this way. So if you want to practice this yourself, you'll eventually get this answer. Okay, let's compare the two oxygens though. Is there a difference in electronegativity between these two oxygen? Well, no, right? Because they're both oxygens, they're the same element. So they're going to share these electrons equally. It's like two people of equal strength playing tug of war. No one's really going to win. They're going to wind up in a sort of stalemate where those electrons are shared equally between them. So if we were to look at the electron density around this molecule, we would see that there's a lot of electron density here in the middle between these two oxygens sharing those electrons. So if I were to draw a map of that electron density, it would look something like this. Okay, kind of like a zombie Stewie Griffin. But basically, there's a lot of electron density here in the middle between those two oxygens, because that's where the electrons are. Okay, now let's compare two atoms. Let's look at a bond where we have two atoms of different electronegativities. So let's say we looked at carbon monoxide. Whoops. There we go. So let's say we looked at carbon monoxide. With carbon monoxide, okay, again, I'm just skipping straight to the answer. You can see how to draw this actually earlier in this PowerPoint, in this video. But if we compare carbon and oxygen in our periodic table, oxygen is further to the right of in our periodic table compared to carbon, which means that oxygen is a little bit more electronegative. It is, well, actually a lot more electronegative, and which means it really wants these electrons more than the carbon does. Now, they're still sharing the electrons. It's still a covalent bond between them, but the oxygen's kind of winning that tug of war. It's pulling the electrons a little bit more towards it. So if we were to look at an electron density map of this molecule, okay, we would see more electron density around that carbon, around the oxygen. So the electrons are kind of sucked towards the oxygen. And this is kind of a very asymmetrical sharing of these electrons. Okay. Now, there are different ways to show this rather than just drawing an electron density map like this. We could, for example, put partial charges. Because this oxygen is sucking electron density towards it, we would say it has a partial negative charge. So we use the lowercase Greek letter delta that looks like that, with a minus sign. Since the carbon is kind of missing a little electron density, we would give it a partially positive sign. Okay, so again, Greek letter delta plus with a positive sign. Another way to show this is to use a dipole moment. Okay, so we draw an arrow or a vector pointing towards our more electronegative atom. Okay, now normally you'll sometimes see people draw it like over the molecule with a different color, or you might see it drawn next to the molecule. I'm going to draw it next to the molecule just so it's easier to see. But this is what a dipole moment looks like. So it's an arrow pointing towards your more electronegative atom. The tail of the arrow is represented with a plus sign to show that partial positive charge on that carbon. Okay, so that's the dipole moment going towards this carbon monoxide, towards the oxygen in our carbon monoxide. So again, I accidentally erased this oxygen over here, but here's the oxygen molecule again, just so you can compare the difference between these. Okay, so it's a little, I haven't really exaggerated much, but notice that here that greatest area of electron density is kind of in between the two oxygens, whereas here it's kind of centered more on the oxygen compared to the less electronegative carbon. So this distinguishes two types of bonds. We have a non-polar covalent bond, also known as a pure covalent bond. This is a covalent bond in its purest form, because remember, we're sharing electrons in a covalent bond, so a pure covalent bond is where those electrons are shared equally. Okay, so when you have two atoms of the same electronegativity, like our two oxygens in an oxygen molecule, that is a pure covalent bond, or a non-polar covalent bond. Okay, because there's not, it's non-polar because neither side is more negative than the other. A polar covalent bond, of course, is where you have a positive and a negative side to that bond. And that is when you have two atoms of different electronegativity sharing those electrons. So it's still a covalent bond because they're two nonmetals sharing those electrons, but the more electronegative of your two atoms is going to pull those electrons towards it a little bit more. Okay. So when it comes to our electronegativity numbers, okay, you probably noticed that we had a scale essentially from 0 to 4. Okay, if, fluorine being the most electronegative element is given a value of 4, and everything else is kind of figured out relative to that. You don't have to memorize these numbers, by the way. It's just a way to help quantitatively compare them. But my point is that you can look at those differences in numbers and figure out the type of bonding you have. So in the case of an oxygen molecule, where they have both your atoms have the same electronegativity, and therefore the difference is 0, that's a pure covalent bond. When you get a difference in electronegativity, okay, so in this case between carbon and oxygen it's a difference of 1.0, that's where you get a polar covalent bond. Now, when it comes to metals bonding with nonmetals, there's such a huge difference in electronegativity that the more electronegative atom, our nonmetal, pretty much wins the tug of war. It's pulling those electrons towards it, and now we've made an ionic bond. Okay, so keep in mind here, this is 2.3, and that seems like a small number, but remember, this is out of 4. So that's a pretty large difference on this scale. Okay, but once again, please don't stress about memorizing these numbers. You can kind of figure this out just from a qualitative standpoint. So typically, as long as you have two different nonmetals, chances are it's probably going to be a polar covalent bond. Okay, now that being said, when we look at our molecules, we have to take into account the polarity of all the bonds involved. So when you want to look at a molecule and determine if it's polar or nonpolar, it might not necessarily be the same as the polarity of the bonds that are making it up. Let me give you an example here. Okay, so let's look at a molecule like carbon dioxide. Okay, so let's draw carbon dioxide out. Again, I'm going to skip to the answer of what carbon dioxide looks like. Okay, it looks like that. I've drawn it earlier in this video, so if you want to practice drawing this from scratch, I recommend it. Now, let's look at each of these bonds individually. So if I look at just this carbon-oxygen bond, just like our carbon monoxide, we're going to have a dipole moment going this way, right? This oxygen over here is partially negative, and so it's going to pull that electron density in that bond towards it. Okay, this is not a pure covalent bond. This is a polar covalent bond, and it's polar pointing towards the oxygen. But here's the follow-up question for you. Is this molecule as a whole going to be polar or nonpolar? And in order to answer that question, let's look at this other bond. Well, this carbon-oxygen bond is going to be polar in the opposite direction. So these actually wind up canceling each other out, and the molecule is nonpolar. Okay, so the molecule as a whole is nonpolar, even though the individual bonds themselves are polar. Okay, so I pointed this out in my lab video, but one quick way to figure this out is to look at your central atom and see what's attached to it. If everything coming off of it is identical, so in this case we have two oxygens, there's no atoms other than oxygen, there are no lone pairs on that carbon, nothing that's not an oxygen coming off of it, you're going to have a nonpolar molecule. As soon as you have something different, so if one of these oxygens was swapped out for, let's say, a sulfur, okay, or if we had a lone pair on that carbon, okay, that would make this molecule polar. Okay, so here's an example now with water. Water is a polar molecule, okay, and the reason for this is that the dipole moments of these two hydrogen-oxygen bonds add up to give you an overall dipole moment going this way. Okay, so here's how that looks like when they add up together. Okay, the two vectors add up, and you have an overall dipole moment. Though again, you could use my shortcut of just looking at that central oxygen and saying, well, it's got two hydrogens and it's got two lone pairs. They're not shown in this picture, but if you were drawing the Lewis structure, you would see them. And since hydrogens and lone pairs are different things, it's going to be a polar molecule. Now, why do we care about the polarity of molecules? The polarity of the overall polarity of our whole molecules will tell us a lot about the type of intermolecular forces that those molecules are eligible for. And understanding intermolecular forces, the attractive forces between molecules, we can understand a lot about the physical properties of those molecules. For example, why is the melting point or boiling point of a particular molecule particularly high or low? We can also understand things like solubility. We'll tackle that in a couple of chapters when we look at solutions. Okay, and we'll notice that intermolecular forces play a big part in that as well. But let's first talk about what these intermolecular forces are. Now, for ionic compounds, the attractive forces between our ions is just positive negative attraction, or Coulombic forces, if you want to use the physics term. Here for covalent molecules, we're going to look at what holds neutral covalent molecules together. Okay, now this can be broken down into three camps. We have dipole-dipole interactions, hydrogen bonding, and London dispersion forces. Okay, now out of those three, hydrogen bonding is the strongest, and London dispersion forces are the weakest. All right, now you'll see in a second that everything has London dispersion forces, but basically we're going to look at molecules that also have dipole-dipole interactions and hydrogen bonding, and that strengthens their attraction to each other. Okay, now out of these dipole-dipole interactions, probably the easiest to explain, so I'll start off with that. A dipole-dipole interaction involves attractions between polar molecules. And so again, you can see why determining if a molecule is polar or not will immediately tell you whether or not it's capable of these dipole-dipole interactions. Dipole-dipole is basically just a interaction between the positive end of one dipole, one polar molecule, and the negative end of another dipole. Okay, it's like the north pole on one magnet attracting the south pole on another magnet. Okay, instead here we have the negative end of one molecule attracting the positive end of another molecule. Okay, so that's pretty much it. You just look at a molecule, and if it's polar, it's capable of this dipole-dipole interaction. Now, hydrogen bonding is kind of like dipole interactions on steroids. They're a special class of dipole interactions that are just stronger because they're so significantly stronger. They have a separate name all to themselves. So what do you need for hydrogen bonding? Well, hydrogen bonding involves a very electronegative element, so either a fluorine, oxygen, or nitrogen, and it needs to be directly covalently bonded to a hydrogen. Okay, hydrogen atoms are kind of special in that they are just pretty much a bare proton with a single electron. So if you have a hydrogen that's connected to one of these really electronegative atoms, that lone electron is pretty much sucked away, leaving that bare proton. Okay, so you have a polar interaction here, but it's so polar. There's a really stark positive charge there on that hydrogen that has no electrons shielding it. Okay, so the dipole interaction you get between two of these molecules is really, really strong because you have this very electronegative atom connected to this pretty much bare proton. All right, so that is what we look for in hydrogen bonding. You want to look for a fluorine, oxygen, or nitrogen, and it has to be bonded to a hydrogen. Okay, it has to be directly covalently bonded to a hydrogen. You can't have atoms in between the two. Okay, then it's not capable of hydrogen bonding. So hydrogen bonding is probably the easiest one to look out for when you've got a molecule in front of you, a Lewis structure in front of you. Just look for a fluorine, oxygen, or nitrogen with a hydrogen attached to it. And if it doesn't have hydrogen bonding, that molecule is going to have one of the other two. It's either going to be a polar molecule with dipole-dipole interaction, or if it's nonpolar, the only option it has available is London dispersion forces. London dispersion forces, which are also known as van der Waals forces, you might hear that term sometimes, they're basically all the same thing. Really, this is a phenomenon that we see in all molecules. Okay, but in the case of nonpolar molecules, it's the only avenue they have to attract other molecules near them. Okay, they're the only attractive forces that these molecules are capable of. So what are London dispersion forces? Well, London dispersion forces are sort of temporary dipoles, or weak instantaneous dipoles that form in these nonpolar molecules. You could think of the electron density around our molecule to be kind of squishy. All right, essentially, this electron density isn't held in place, but it kind of moves around a little bit. Okay, so let's say in a molecule we have it squished to one side, squished, let's say, to the right. So if we look at our molecule over here, let's say the electron density gets squished a little bit to the right. So the right of this molecule is slightly negative and the left becomes slightly positive. Now, if this side is slightly negative, what's it going to do to a nearby molecule? Well, these negative electrons are going to repel the negative electrons in this molecule, okay, and so it'll cause them to squish to the right of this molecule. Well, what does that do? Well, it makes the right of this molecule partially negative and the left of it partially positive. So now notice that for our molecule on the left, the right of it is partially negative. For our molecule on the right, the left of it is partially positive. There's going to be a slight interaction here between this partial negative and this partial positive. Now, I have to stress here, this effect is very weak and very temporary. Okay, this squishing of electrons to one side, we have a partial negative and a partial positive. It's very, very partial. Okay, it's a very small effect. and it doesn't stay there. It's only a temporary squishing. So again, this is not a permanent change. Like our polar molecules are permanently polar. Okay, but here in London dispersion forces, our nonpolar molecules are only weakly and temporarily polar. Okay, but that's what London dispersion forces are. They allow this sort of weak temporary polar interaction for these nonpolar molecules. Okay. Now that being said, the larger your molecule, the more electrons you have to play around with, the more electrons you can sort of squish to one side, and therefore the more that the more that this effect increases. Okay, so that's why it's possible to have nonpolar molecules that do have higher melting points and boiling points because they have so many electrons to play around with. So to give you an example, iodine, okay, an iodine molecule, which is diatomic, you have two iodine atoms bonded to each other, those have a lot of electron density because iodine's a huge atom, right? So iodine, if you look at iodine crystals, they're solid at room temperature. So when I say iodine, don't think of iodine solution that you use on cuts. I'm talking about like pure iodine. It's a like a purplish, like a dark purple crystal. Okay. Again, this is my point here is that even though it's a non-polar molecule and it only has London dispersion forces, because there's so many of these London dispersion forces, it's able to be a solid at room temperature. Okay, so that brings us to the effect of these intermolecular forces. As I pointed out, with the strength of these, we see effects on the physical properties. So you have polar molecules that have dipole-dipole interactions, hydrogen bonding, and so on. They have really high melting points and boiling points relative for molecules of their size. Okay, they also have high heats of fusion and vaporization accordingly. Okay, whereas nonpolar molecules, which only have London dispersion forces, have much lower melting and boiling points and much lower heats of vaporization and fusion. Okay, of course, these dwarf compared to ionic compounds, which, that positive negative attraction and that huge network of it in your crystal lattice, that results in really high melting and boiling points. But hydrogen bonding is no slouch. If you look at a water molecule and you say like, its boiling point's only 100 degrees Celsius, its freezing point's only 0 degrees Celsius, that's actually pretty impressive for a molecule the size of water. Water is a really tiny molecule, and a molecule of that size should be a gas at room temperature. The fact that it's a liquid at room temperature is kind of amazing, and it's really the hydrogen bonding that's responsible for that. Okay, so so basically it comes down to that concept. You want to look at your molecules and basically first ask yourself, does it have hydrogen bonding? And if if it has a nitrogen, oxygen, or fluorine connected to a hydrogen, then yes, it's got hydrogen bonding. If no, then you can take it one step further and ask yourself, like, well, is it polar or nonpolar? If it's polar, it'll have dipole-dipole interactions. If it's nonpolar, then it's going to have only London dispersion forces. All right, so let's try an example here of some of these, if we had a problem like this. So let's actually take, example here with ammonia, right? So if we look at an ammonia molecule, so if I drew that out, it would look like this. Okay, so we want to determine what type of intermolecular forces we're dealing with here. Okay, so first ask yourself, is this capable of hydrogen bonding? So remember, to check for this, you have to have a nitrogen, oxygen, or fluorine, and it's got to be directly bonded to a hydrogen. So here we have a nitrogen, so it means that, and it's connected to a hydrogen. So yes, this has hydrogen bonding, and we're kind of done with that. We know that the answer for the type of intermolecular force here is hydrogen bonding. Okay, let's look at a different example. So let's look at acetone. So here's the Lewis structure for acetone. Okay, it's a carbon double bonded to an oxygen and connected to two hydrogens. So first of all, ask yourself, is this capable of hydrogen bonding? So does it have an oxygen, nitrogen, or fluorine that's connected to a hydrogen directly? It has an oxygen, but is there a hydrogen that's connected to that oxygen? No, that oxygen is only connected to a carbon. It's not directly connected to the hydrogens on this molecule, so this does not have hydrogen bonding. So now the next question you should ask yourself is this molecule polar or not? So we look at that carbon, let's see what's connected to it. We've got a hydrogen, hydrogen, not a hydrogen. We've got an oxygen here. So this is going to be a polar molecule, which means that it's going to have dipole-dipole interactions. Okay, so that's how you kind of proceed from an example or Lewis structure of a molecule and determine if it's got hydrogen bonding, or if it's got dipole-dipole interactions, or if it's got only London dispersion forces. Okay, so if we had a nonpolar molecule, the answer would be just London dispersion forces. Okay. So here's some suggested homework for this chapter. So please do try out all these problems. As I pointed out, we've learned a lot of rules and a lot of procedures here for how to draw molecules, to how to name them, how to write out their formulas, how to determine their shapes, how to determine whether they're polar or nonpolar, how to determine their intermolecular forces. So I really recommend practicing this stuff. The more you practice it, the more automatic it becomes and the easier it will be on a quiz or exam. Okay, so be sure to try this out. Definitely, if you haven't finished that lab report, please do the lab report, compounds and their bonds. The table at the end will definitely get you to practice drawing Lewis structures and determining shapes from Vesper theory and determining polarity. Okay, now the next thing we have is an exam. So we have an exam covering chapters 4, 5, and 6. So please go through your quizzes for chapters 4, 5, and 6, just like we did with exam 1, which was on chapters 1, 2, and 3. So here, again, you want to look at your answers for your quizzes on chapters 4 and 5. So be sure to do that. Just go back to to Blackboard, look at your old quiz scores under Check My Grade, or I think it's Check Your Grade. When you click on the score, it should be able to give you feedback on the quiz, and it'll tell you what the right answers are. And in a lot of cases, I've explained why the answers are what they are. And of course, you're always welcome to ask me about your quizzes. Okay, go back through those quizzes on chapters 4 and 5. Determine what you got wrong. Determine why you got it wrong. Make sure you get that type of question right on the exam. Okay, you want to practice that stuff. With question 6, since we're obviously not taking a quiz on that, there is a practice quiz available on Blackboard. I highly recommend trying it out. The answers are at the end, so again, you can grade yourself. You can see what you need to work on. Make sure you practice that material, get it right on the exam. All right. So that being said, let me know if you have any questions, and good luck.